Welcome to our third and last sequence of videos. Today we're going to present our latest results using our FWIME algorithm. We're going to show you some more realistic and exciting numerical examples that span a wide range of scenarios bearing different types of challenges. Since this year's meeting is online, we want to first introduce ourselves. This picture was taken in our windowless office at Stanford University. My friend Ettore, on the left, is from Genova in Italy, and I am from Nice, France. In the past 4 years, Ettore and I have been working as a team and have tackled many different projects together. And today we're really excited to show you our latest results with FWIME. Before we start this presentation, we would like to invite you to visit and subscribe to our YouTube channel called EG Optimization, where you can access our updated work, which includes our results on FWIME and target-oriented elastic FWI. Also, the presentation you're currently watching will be uploaded on our YouTube channel next week. Let's go back to our main storyline and see where we stand. We are now in part 3 called Benchmark Numerical Test, and we're going to focus on 3 different tests. First, the well-known Marmousi2 model, then the North Sea region of the BP 2004 model, and finally, we will test FWIME on the syncline model proposed by the SciScope consortium last year. Before we dive into part 3, we want to provide you with a quick recap from the first 2 parts, since some of you may have forgotten the main takeaways. If you remember everything, you're welcome and encouraged to skip this part and directly go to slide 19. Okay, so the first part was called Theory and Design and gave some more insight on how we built our FWIME objective function. The objective function is composed of 2 terms. First, a data fitting term, which is a modified FWI objective function, and second, a wave equation MVA term. In the data fitting term, we add a data correcting term to ensure phase alignment between observed and predicted data. And this data correcting term is obtained by applying the extended Born modeling operator B tilde to an extended perturbation P tilde optimal. We saw that P tilde optimal, or P tilde opt, is computed iteratively every time our velocity model MI changes. And such computation is referred to as the variable projection step in FWIME. We also saw that P tilde opt possesses similar features as extended images, which can provide valuable information about the accuracy of our velocity model. Our modified and invertible DSO operator plays a key role in the MVA term. By enhancing the energy present in P tilde opt, it contributes in guiding the FWIME towards the global minimum. Finally, the trade-off parameter epsilon balances the relative contribution of the 2 terms, and this parameter is selected once and for all at the beginning of the inversion process. So after getting better insight on the structure of our cost function with part 1, we showed you how we minimize it, and this was the topic of part 2 of our video lecture series. So in part 2, we began by analyzing the FWIME gradient, and we showed that it is composed of 2 terms. First, a Born component that shares similar features with the FWI gradient, and second, the tomographic component that is key to update the crucial missing low wave number components at early stages of the inversion process. We then explained the importance of combining our model space multiscale method that we presented at the last SCG annual meeting with our FWIME scheme. In this method, we parameterize our unknown velocity model on sparse grids using B-spline basis functions. We simultaneously invert the full data bandwidth while gradually refining the spline grid with iterations. The inverted model for a given grid is then used as the initial guess for the following inversion performed with a finer grid. In fact, this slide shows the sequence of FWIME inverted velocity models on the 4 different spline grids used for the Marmousi2 numerical example we're about to show you. The key here is that the grid refinement rate allows us to better control and slowly increase the wave number content of the model updates. And though more computationally costly than a conventional data space multiscale approach, this method allows the FWIME gradient to leverage all the events in the data, including reflections, to recover the crucial low wave number components from the start. And as we mentioned and showed in part 2 with numerical examples, this model space multiscale technique is necessary for the success of FWIME. Okay, we are now ready to tackle the third and last part of our lecture series, where we test FWIME on benchmark numerical examples. And the first test is conducted on the well-known Marmousi2 model proposed by Martin et al. 2006. We begin by a brief description of the experiment setup, and we summarize the main challenges associated with this numerical example. Indeed, we show that conventional data space multiscale FWI fails to retrieve a useful solution. And finally, we show that our FWIME workflow is able to retrieve an excellent solution. Furthermore, we will closely examine all the different components of our cost function, and we will show you that their behavior is in agreement with our theory. Moreover, for the other numerical examples presented after this Marmousi2 model, we will adopt a similar presentation structure. This panel shows the Marmousi2 synthetic model, which is approximately 17 km wide and 3.5 km deep. We generate a noise-free synthetic dataset with a surface acquisition where we set sources every 120 meters and receivers every 30 meters, and we record the data for 8 seconds. The maximum offset recorded is approximately 16 kilometers, and we use a source containing energy restricted to the 4 to 13 Hz frequency range. And finally, our modeling is conducted with an acoustic isotropic engine, which is also used for the inversion process. The first main challenge is the lack of low-frequency energy in our seismic source, whose spectrum in decibel is displayed here on this graph. The second challenge is the inaccuracy of our initial model, which is laterally invariant and with values linearly increasing with depth. And this panel shows the initial velocity model used for both conventional FWI and FWIME, which is, as we can see, very inaccurate. Indeed, this is confirmed by examining these three panels showing depth velocity profiles of the true model with the blue curve and the initial model with the black curve, extracted at 3 different horizontal positions. Finally, the dataset is mostly composed of reflected events and contains very little refracted energy, which we know is very useful for the success of conventional FWI. This shows 2 representative shot gathers for sources positioned at 0 and approximately 8 kilometers. And as previously mentioned, they are mostly composed of reflected energy. So we conduct conventional data space multiscale FWI using 5 different frequency bands spanning the 4 to 13 Hz frequency range. We do not conduct any offset continuation, and we begin with the same initial velocity model described in the previous slide. As expected, the lack of low frequency energy combined with the inaccuracy of the initial model leads FWI to converge to a non-useful local minimum. Let me now flip between the FWI inverted model and the true Marmousi2 model to better assess the inversion results. We now apply our model space multiscale FWIME workflow. The same initial model is used for the inversion, and the full data bandwidth is simultaneously inverted, and all the events present in the recorded data are injected from the start. To be clear, we do not select or separate reflections, refractions, and direct arrivals. We use a time lag extension ranging from negative 0.3 seconds to 0.3 seconds to account for the large kinematic errors stemming from the inaccuracy of the initial model. Our model space multiscale approach is performed with 4 spline grids. We assume no prior knowledge of the subsurface, and we use a sampling for the first grid of 900 meters in the x direction and 200 meters in the z direction. At each refinement step, we decrease the sampling in both directions by a factor of 2. And the 4th spline grid, which is the final grid, coincides with the finite difference grid. Moreover, our trade-off parameter epsilon is selected at the initial step and is kept fixed throughout the inversion process. As you will soon discover, our inversion was conducted using 240 iterations of LBFGS for the nonlinear part and 60 iterations of linear conjugate gradient for the variable projection step. We applied no illumination compensation, and we used a gradient mask in the shallow region of the water layer down to 350 meters to refrain the inversion from updating the water layer. In the following, we're going to guide you through our inversion process, and we're going to dissect the different terms involved in the FWIME scheme. We begin by analyzing or examining the initial search direction, and we illustrate the benefit of the spline parameterization. The left panel shows the scaled initial FWIME search direction on the finite difference grid, and the right panel displays the ideal search direction, which is the difference between the true and the initial models. We can see that some of the low wave number features are definitely captured in the shallow region of the model on the left-hand side, but are hampered by high wave number features likely to be inaccurately located. After mapping the FWIME initial search direction on the first spline grid, we can see that on the left panel, most of the high wave number features have been removed and the low wave number components now dominate. The right panel shows the ideal search direction also after applying the mapping onto the first spline grid. And we can see that our initial FWIME search direction now manages to capture those low wave number components of the true search direction and seems much more promising than on the finite difference grid. We want to mention here that we did try to apply FWIME without our model space multiscale approach. That is, by directly parameterizing the velocity model on the finite difference grid from the start, and we did not manage to recover an accurate solution. Therefore, we really want to insist on the fact that FWIME does require the model space multiscale approach to work properly. So now that we have obtained a promising search direction, we conduct our model space multiscale FWIME workflow. Okay, so now we're going to show you the sequence of our FWIME inverted models. Each panel will correspond to the last inverted model on a given spline grid. And as we mentioned earlier, we used 4 different spline grids, and the 4th grid coincides with the finite difference grid. Moreover, each spline grid refinement is triggered when the stepper is unable to find an appropriate step length for that particular grid. So this is the model inverted after approximately 25 iterations on the first spline grid, and only the low wave number features have been updated because the grid is quite coarse. This shows the FWIME inverted model after approximately 55 iterations on the second spline grid. We can see that some sharp interfaces have already been added due to the finer grid sampling, and moreover, the inversion seems to be going in the right direction. And this is the inverted model after 100 iterations on the third spline grid. The model already looks quite accurate, and most of the main features have been recovered. And this is the final FWIME inverted model. The recovered model is excellent, but does slightly suffer from edge effects inherent to the limited acquisition aperture. And to compare, this is the true model. I will now flip between the two panels in order to assess the quality of our result. And now we're going to assess the quality of our inverted model at 3 key horizontal positions: 8 kilometers, 11 kilometers, and 13 kilometers. These 3 panels are depth velocity profiles extracted at x equals 8, 11, and 13 kilometers. The initial model is represented by the black curve, the true model is shown in the blue curve, and the inverted model is in the red curve. We can see that our recovered solution is excellent even in the deeper regions of the model. The next step is to analyze our inversion process, but from the data space perspective. The left panel shows the observed data for a shot located at a horizontal position of 1 kilometer. The middle panel is the predicted data computed with the current velocity model estimate, showed in the panel located in the top right part of the screen. And here the velocity model is the initial model. Finally, the right panel is the difference between the observed and predicted data. And each panel is displayed with the same grayscale. And now we're going to show you a sequence of 4 slides corresponding to the predicted data and data difference computed with the inverted FWIME velocity models obtained after each spline grid. So after the inversion on the first spline grid, we can already see that part of the refracted energy in the predicted data in the middle panel begins to better match the one from the observed data. And moreover, no reflection are present in the predicted data yet. After the inversion on spline 2, most of the refracted energy is now correctly captured, as we can see in the middle panel. Moreover, the more finely sampled spline grid allowed the model updates to introduce sharp interfaces into the model, thereby creating reflected events that can be observed in the predicted data shown in the middle panel. The inversion on the third spline grid has already provided an accurate velocity model, as we can see in the top right panel of the screen, and the data difference shown in the right panel begins to vanish. The final FWIME inverted model shows an excellent recovery, and the data difference shown on the right panel vanishes. Now let's take a closer look at what our p-tilde optimal looks like throughout the life of our FWIME inversion scheme. If you remember from part 1, p-tilde optimal should completely vanish once an optimal solution, i.e. the true velocity model, has been reached by our inversion. Also, since p-tilde op possesses similar features as conventional extended images, it serves as a crucial quality control or QC tool that provides important information about the level of accuracy of our current inverted model. And in a 2D world, p-tilde optimal is a three-dimensional hypercube where the third axis corresponds to time lags for this numerical example, represented by tau. Again, if our FWIME works correctly, this guy should eventually completely vanish, and indeed, this is exactly what we're going to observe. In the next sequence of slides, we're going to examine two components of p-tilde optimal after the inversion on each of the 4 spline grids. The first component we're going to look at is the zero lag cross-section, also referred as the physical cross-section, if you remember from part 1. Then we will examine a time lag common image gather from p-tilde optimal extracted at a horizontal position of 12 kilometers, shown in the right panel on the screen. And all panels are displayed with the same grayscale. This shows p-tilde optimal computed with the initial velocity model shown in the top right panel. On the common image gather in the right panel, we can see plenty of energy located far away from the physical axis, which indicates that our initial velocity model is extremely inaccurate. After the first spline grid, we can see that the energy within p-tilde optimal has begun focusing in the vicinity of the physical axis where tau equals 0, as we can see from the common image gather. This indicates that our velocity model has improved in accuracy. After the inversion on the second spline grid, the zero lag cross-section becomes more focused, which is confirmed by the time lag common image gather on the right. Most of the energy is located in the vicinity of the physical axis, and moreover, as you will see, the inverted model at that point is already accurate enough for conventional FWI to converge to the global solution. After the inversion on the third spline grid, p-tilde optimal has almost completely vanished, and the inverted model is quite accurate. Finally, our last inverted model is excellent, and as expected, p-tilde optimal has totally vanished. And finally, the last component that we're going to examine from our FWIME workflow is our cost function. This plot shows the total FWIME objective function as a function of iterations. The final convergence is reached after approximately 240 iterations of LBFGS. The 3 sharp discontinuities in the rate of convergence occurring at iteration 24, 88, and 192 indicate a spline grid refinement, and each spline grid refinement was triggered when the solver failed to find a step length that would decrease the objective function value. As we're currently implementing our 3D code, we're trying a few tricks that may improve the convergence rate of FWIME. We recommend to subscribe to our YouTube channel, EG Optimization, as we will be soon posting more updates as we get closer to making these adjustments and tricks work for our 3D field data application. As we explained in our report, FWIME should not be conducted until full convergence as we did for this numerical test. Instead, it should be used to provide an accurate enough starting model for more conventional and less computationally demanding techniques, such as FWI. In fact, if we conduct conventional FWI using the inverted model on the first spline grid, we can already recover an excellent solution. So here, basically, after 25 iterations of FWIME, we can already obtain an accurate model with conventional FWI. And this is the model obtained after conducting FWI using the FWIME inverted model on the second spline grid as an initial guess. Finally, this is the analogous result using the FWIME inverted model on the third spline grid, and we can see that it is almost identical to the final FWIME inverted model. The red curve on this plot corresponds to the value of the conventional FWI objective function evaluated at each FWIME inverted model, and it is not the result of an inversion process. As expected, it is also not monotonically decreasing, which illustrates that the FWIME algorithm has successfully created an alternate descent path towards the global minimum that could not have been taken by conventional FWI. So this is the end of our presentation on the Marmousi2 model. We hope that you enjoyed this numerical test, which was the first realistic example where we managed to successfully apply FWIME. And we really tried to make this process as user-friendly as clear as possible in order to show the potential of our technique at reaching a broader range of non-expert users. Now that we illustrated how we can invert a dataset dominated by reflected event, we will next show you how FWIME can invert a dataset dominated by diving waves on the North Sea region of the BP 2004 model.